Hello everybody. Today we have lecture number 15 and we continue our discussions in the frame of chapter 7 about topologies. So the basic topology is this one and special cases are weak and weak star topologies. So first of all, I would like to summarize what we have already discussed last time. So it is in this slide. So the setting is as follows. We have a vector space E over field K, real or complex numbers. F is a subspace of E star, which is an algebraic dual to E, but not an arbitrary subspace, but a subspace which separates the points of E. So we have discussed last time that we can create a topology denoted by this symbol. It is a topology on this space E, and it is given by linear functionals from this subspace of algebraic dual F. So the basic neighborhoods of points have this form in this topology. So for arbitrary point A, arbitrary positive epsilon, and arbitrary finitely many linear functionals from F, we have this formula. That is, it is all points in E such that so finitely many, so these finitely many inequalities are true. And we have proved last time that this basic sets, basic neighborhoods of points, so they give us a topology, which is all open sets, and these topologies are arbitrary unions of such basic sets. And we have shown that this topology is Hausdorff topology, and moreover, the convergence in this topology looks as follows. So xn converges, so sequence xn converges to x in this topology in E, if and only if it converges coordinate-wise, where as coordinates we consider all linear functionals from F. So let me specify this line. It is an important line, and moreover, this topology is chosen in such a way that actually the topological dual to this topological vector space, so it is a vector space endowed with some topology. It's a topological vector space. Its topological dual is exactly F. Okay, this we have discussed last time. Moreover, now we can exchange the roles of E and F in the following way. So we consider F as points, and to each point X in E, we make consider this functional. This functional is a point evaluation which acts on F head of X, so point evaluation at the point X. So hence each point X in E gives us a linear functional on F. So we have exchanged the roles, and then we may do the same procedure. So I have clarified last time that when we change the roles, then it turns out that this guy separates the points of F. So we are exactly in the same setting as here, but with exchanged roles. And hence we may create in the same way the topology, but the topology on F, so topology Fe on F. And the convergence in this topology will look as follows. So a sequence of linear functionals Ln converges to L in this topology on F, if and only if the linear functionals converge pointwise on E. So let me mark this line. So if you compare these two lines, you see that condition looks very similar here. But here this happens for all, so convergence is in E, and this condition holds for all elements of F. And here vice versa, here convergence is in F, and this condition holds for all elements in E. So probably it will help you to remember, to memorize the convergence in both topologies. And again, so this topology, again, due to this theorem, nothing else, is such that the topological dual to F endowed with this topology is exactly this space, which is isometrically isomorph to E. So we have this scheme, and I think this is helpful to see this picture, to store this picture in your head. So we have E, and then the topology sigma EF here, and we have F, and the topology sigma FE here. So E and F, and here F and E. Okay, so this is the basic scheme, and now we consider special cases. So last time we have discussed first special case, example 7.4. So now X is a norm space. That is, we have a vector space and a topology given by the norm. So we forget, okay, so having this, we have a topological dual. So take E to be X and F to be topological dual. Of course, if we have an infinite dimensional norm space, then topological dual is a subset of algebraic dual. So we are in the setting as before. And we have already studied that topological dual separates the points of X. So we are exactly in the setting where we can create this topology, sigma EF. So this topology in this particular case is called the weak topology. And having all the results about this sigma topology in general, we conclude that the norm space endowed with this topology, sigma X star, its topological dual is exactly X star. That is, we had a norm space and we had its topological dual. Now we have changed the topology, but in a way that the topological dual is preserved. And we also clarified last time that if dimension of X is infinity, then this topology, which is called weak topology, is strictly weaker than the topology generated by the norm, also known as strong topology. Okay, so in this particular case, this weak convergence looks as follows. Follows exactly from what is written here. Okay, and so strong convergence implies weak convergence because strong topology is stronger, or at least not weaker than the weak topology. Okay, it was last time. Now we go further and we consider example 7.5. Again, X is a norm space. Hence, we may consider SE X. And as F, we may consider its topological dual. That is the dual, a topological dual to this space, to this topological vector space. Okay, and hence now we may consider the sigma FE topology on F. That is in this picture. So if we have X here and X star here, then the topology here is called the weak topology. And now we are discussing this topology, and this is called the weak star topology. So this is a topology on X star, which is constructed having on the base of X star and X. And again, using all the results about this general case, sigma EF, we may conclude that this topology has the following properties. Oh, first of all, yes, so this picture, so in this special case, so this is my E, this is my F. Here we have the topology sigma EF, which is called weak topology. And here we have the topology sigma FE. And in this particular picture, it has the name weak star topology. Okay. So again, so the convergence in weak star topology is as follows. So linear functionals Ln converge to L in this topology. This would be the notation. So this is for weak and this is for star. So I suggest to you to dictate me what I should write. So what does mean that Ln converges to L in this weak star topology?
For arbitrary x, Lx converge to Lnx converge to Lx. X belong to
Yes,
capital X.
yes. Let us check. Yes. Okay, so now a little bit step forward. So in one hand, we have this weak star topology, which is in this picture in the right, so in the right hand side and below, so in this right low corner. But on the other hand, this is a norm space. So it has its topological dual. This is X star, and then it dual to it's X2 stars. And then I may consider, so this is my E. So probably let me write down. So this is my E, this is my F, and then here again should be the topology sigma EF. And then this is not the same topology as this one. This is the topology which is denoted like here. And it is, yes, it is called weak topology on X star. Okay, so if we consider this picture, then this topology is the weak star topology. It's related to this guy. But if we consider this picture, there is the topology, which is the weak topology, and it is related to, so it is in the left corner, not in the right corner. So what does it mean? This means that on this space, we have two topologies, and it would be nice to compare them. So if X is reflexive, that is, we have that the canonical mapping of X is X2 stars, then this topology, weak topology on X star, is the same as weak star topology. Yeah. So once again, we have two topologies here on X star, but since X2 stars and X are related in this way, in the case of reflexive space, then these are the same topologies. So if X is a reflexive Banach space, then the weak and the weak star topologies on its dual, topological dual, they are the same. Okay? Probably I can mark it like we have this, and we use it here. Okay, so if X is not reflexive, then the weak the weak star topology, so this one, which relates to this guy, is strictly weaker than the weak topology, which relates to this guy. Because if X is not reflexive, then this guy is bigger than G of X. That is, we have more more coordinates which we have to control, or more linear functionals which we use for the construction of the topologies. So the weak star topology is strictly weaker than the weak topology in the case when our X is not a reflexive Banach space. Is it clear so far what's going on?
I think yes.
Okay. Good. Examples. So let us play with some particular examples to see what happens. So first of all, let us consider the space LP for P from 1 including 1 to infinity including infinity. In this space of sequences, LP, we may consider this Schauder basis. These are vectors with coordinates, E1 is 1, 0, 0, 0, etc., and so on. And the nth vector, En, has all coefficients coordinate 0 except the nth coordinate. So this is the nth coordinate. Okay, so I hope it is clear for you that such sequence of vectors in this space does not converge in the norm of any LP. Agree?
Yeah, it's not a Cauchy sequence.
Yes, it's not a Cauchy sequence. But now we may weaken the convergence. So statement number 1. So we consider P between 1 and infinity without 1 and without infinity. Then the statement is that this sequence converges weakly to 0. Converges weakly and the limit is 0. So this is the statement. So we have this case. We have weak convergence. That is this my X. It is E or F. This is my question to you. What is my E? What is my F here in my construction? Then we have LP, and we discuss weak convergence in LP. So what is my X, LP? It is E or F?
LP is E.
Yes. So this is my LP. Probably I have it down here. So what is then my F?
The topological dual of LP.
What is it?
All the continuous and linear functional on LP.
Yes, but in this particular case, we know,
Uh,
okay, at least, okay, we know, of course, like this, but we may say LQ. Yeah, where 1 over P plus 1 over Q is 1.
yeah.
Yes. So for any L which belongs to my F, which is LP dual, we have that this L corresponds to, so L is equal to LA for some A in LQ. That is, sorry, my L acts on X in the following way. This is the sum, K from 1 to infinity, AK, XK. A, it is a vector with coordinates, and X is also the vector with coordinates. X from LP and A from LQ, yes? Hence, how L, this linear function L acts on these elements of this sequence. L applied to En is as follows. The sum K from 1 to infinity, AK, times kth coordinate of vector En. But this is nothing else but An. And this converges to 0 when n tends to infinity, since A belongs to LQ. That is the sum of AK to the power Q is finite. So if the series is finite, then the tail, so it's not the tail there. So if the series converges, series of positive non-negative numbers, then the numbers themselves converge to 0. And hence we have that An converges to 0 when n tends to infinity. It's clear?
Yes.
Yes, but this 0 can be interpreted as L of 0 because L is a continuous linear functional. So for any linear functional, we have this identity. So we have shown what we have shown. We have shown that for any L belonging to F, I don't like the color, for any L, we have that LEN converges to L0. That is, we have this. Agree?
Yes.
Okay, let us consider next case. Case P equal to infinity. So in this case, the statement is that this sequence converges weakly star to 0. So weakly star, what does it mean? So what is my E in this story? What is my F in this story?
E is LQ. F is LP.
Yeah, so LP is my L infinity. It is E or F?
F.
F, yeah, so this is my L infinity. So what should be my E?
L1.
L1, okay. Okay, and we are interested in the so in this So convergence is in this topology, weak star topology. Okay, so so let me check that it is so. Again, what does mean that we have a weak star topology convergence? This means that for any x, x1, etc., xn in L1, consider consider En of x, or equivalently gx of En, and how it acts. It is a sum k from 1 till infinity. En kth coordinate times xk. And since En is like this sum is nothing else but xn. And this again converges to 0. Converges to 0 as n tends to infinity, since my x belongs to L1. That is, the sum of absolute values of xk is finite. Again, since the series is convergent, the summands should tend to 0. Yes, but what we have shown that for any x in this E, this guy converges to 0, which is again, what is it? So 0 linear functional evaluated at x. Yes, so these linear functionals, En, now they are linear functionals on L1. They converge pointwisely on this set L1. They converge pointwisely to 0 linear functional. That is, we have this convergence. Is it clear?
I think yes.
Okay,
But
so
I just say a little complicated, but it's okay.
Okay, so you always have to apply this general scheme, and then all the pieces of information will be placed in the proper place. Okay. Now, last case, P is equal to 1. Then the statement is that this sequence of vectors does not converge in the weak topology. So again, weak topology, that is as here. That is again, we have as E, we consider L1, so this my space, X. And then as F, I consider its topological dual. And I am interested in the topology here. So the statement is that this sequence of vectors does not converge in this topology. So how to check? Indeed, consider A, which is the vector of this form, 1, 1, etc., only once. This is a nice vector in L infinity. So here. Hence, if we apply LA, which belongs to this E topological dual, if we apply to, okay, acts as follows on the elements of my sequence. So LA applied to EN, you will get 1. And this is for any n in natural numbers. That is, EN does not converge to 0 in the weak topology. So I have to write down this weak topology. So again, in order to converge weakly in 0 to 0, this means that for any linear functionals from here, so these coordinates, so the coordinate which is described by this linear for any linear functional, so any coordinate which corresponds to a linear functional from the topological dual space, we should have that L of En converges to L of 0. But this is not the case. We have this counterexample. Okay.
Okay.
Now my question to you. P is equal to 1. So the question is, can we say that En converges weakly star to 0? This is my En. So we have specified that the weak star convergence is, in infinite dimensional situation, is strictly weaker than the weak convergence. So if there is no weak convergence, probably in the weaker sense, there is some convergence. In particular, what about this convergence? So what should be the picture? What is E? What is F? And if weak star, so we are interested in this convergence, in this topology. So what is my E or what is my F?
E is L infinity and F is L1.
No, F is L1, so this is my space. Yeah.
Right.
But E should be such that L1 is its topological dual. So E should be C0. So the space of finite, the space of all sequences which converge to 0. Yeah, then this is its topological dual, okay, like this. And hence, this would be the weak star topology. Okay?
Okay.
Yes. So in order to have weak star topology, what should we have? We should have that En of x converges to 0 of x when n tends to infinity for all x's from this space C0. So what would you say? Is it true or not?
Yeah, it's true.
It's true, because here we have only sequences or elements whose coordinates converge to 0. Okay, so hopefully this example will help you to orient in all these weak and weak star topologies and convergences. So once again, if we have an infinite dimensional space, so on its dual, we may consider weak topology, so on its dual topological dual, we may consider the norm topology generated by this norm in the original space. Then the weak topology, and then the weak star topology. So we have even 3 topologies, and so the strongest is the topology generated by the norm. The weakest among all of 3 is the weak star topology. Okay. Yeah, so it was my question, but we have already clarified. So this is a remark that weak limits are unique, and this is an exercise for you to check that this is the case. We do not discuss it further, just for you to know. Okay, and then theorem 7.8. So let X be a norm space, then each weakly convergent sequence in X is bounded with respect to the norm. And if X is a Banach space, then each weak star convergent sequence in X star is bounded with respect to the norm on this topological dual. So once again, for a norm space, this is also a norm space, we have strong topology, that is a topology generated by a norm, this one or this one. And we have also a weaker topology, for example, weak topology or weak star topology. So since when we consider weaker topologies, we have more convergent sequences. Okay? And sometimes in applications, it's just easier to construct by hand, so to say, or present constructively a weakly convergent sequence or weak star convergent sequence than a sequence which converges in the norm. So the question is, if we have a sequence which converges weakly or weakly star, can we somehow upgrade this convergence and state something, claim something in terms of the strong topology, that is in terms of the norm? So this is the, so to say, the aim, and this is what is usually needed in calculus of variation. So of course we would like to work with norm spaces, that is with strong topologies. But yeah, technically it's easier to obtain some weakly convergent sequences or weak star convergent sequences. Can we upgrade? So can we obtain some information from weakly convergent sequence about this sequence in the norm? So this theorem is like a okay, first step in this direction. So if we have a weakly convergent sequence, that is a sequence which converges in the topological space, vector space X, with weak topology, nevertheless, it is at least bounded in the norm, in the strong topology. Okay, so this is the statement. Let us prove it. So, and we start to prove with point 2. So we are working here. So we have a weak star convergent sequence. So let Ln converges weak star to L in X star. What does it mean? This means by our previous discussions that the linear functions converge pointwisely in X. But what does it mean? This means that for any fixed X, this sequence Ln, yes, I understand that my L looks very similar to E, but now in this proof we don't have E, only L. Ln of X. This sequence is a sequence of scalars. That is, this sequence converges, okay, is convergent in K, in our field of scalar. So in real numbers or in complex numbers. But in this case, we know that if we have a convergent sequence of scalars, then this sequence is bounded. Is bounded in K. That is, we take supremum over all n, absolute value Ln of X. It is smaller than infinity for each fixed X in X. Is it clear so far?
Yes.
Okay. But what does it mean? So therefore, so what does mean this condition? This means that the sequence of linear functionals, so this set, the sequence of linear functionals, probably let me write down exactly the word the set. Therefore, the set of the linear functionals, that is mappings, from Banach space X to normed space K is pointwise bounded. Hence, by the uniform boundness principle, I guess it was theorem 2.32. So uniform boundness principle, we have that supremum of norms of all these linear functionals is also finite. Yeah, so this is where we use this one of very few important results about linear analysis in Banach spaces. So we have pointwise boundness. From this we obtain, via this uniform boundness principle, the boundness of the norms. But what does it mean? This means that is the set Ln is bounded with respect to this norm. Supremum is equal to some constant, which is finite, and hence this set is a subset of a ball around 0 in this space, whose radius is exactly this supremum. Okay. Do you still remember what does mean that a set is bounded in some normed space?
Yes.
Yes. Okay, so we have shown this item number 2. Now we have to show item number 1. May I go to the next slide?
Okay, please.
Well, item number 1 in a similar way. So what does mean that sequence xn converges weakly to x in our norm space x? This means that L of xn converges to L of x for any L in x star. But again, what does it mean? This means that the sequence Lxn is bounded in K for any L from this set. And hence, if the sequence is bounded, so we can rewrite it in this way. Supremum n over n, absolute value of L of xn is finite for any L in x star. But this guy is nothing else but point evaluation at the point xn. Yeah, so this linear functional which acts on x star. That is, this condition can be rewritten in the following way. That is supremum over all n, absolute value, so this absolute value is smaller than infinity, and this holds for any L in x star. And again, this means that this sequence is pointwise bounded on x star, and hence again by the principle, uniform boundedness principle, I shorten it, uniform boundedness principle. We obtain that supremum over all n in n norms of gxn norm in this space is finite. Okay. Everything is clear so far?
Yes.
Yes. Okay, since J, which maps x into x two stars, and point will be mapped onto this mapping, point evaluation. So since this mapping is an isometry, not necessarily isomorphisms, but just an isometry, then we know that the norm of Gx in this space x two stars is the same as the norm of x in the space x. And this happens for any x. Hence this can be rewritten in terms of norms of xn. Hence, supremum n over n, norms of xn, norm in x, is finite. That is, the sequence is norm bounded. This is what we wanted to show. Yeah. So again, we have used the uniform boundedness principle and playing with passing from x to its image in this B-dual space. Okay, so is everything clear? Or do you have any question?
It's clear.
Okay, then we go further. Theorem 9. So let X be a norm space, then first statement. So if we have a sequence in X which is bounded, and there exists a dense set such that so dense set of dense subset of topological dual, such that for all coordinates from this dense subset, we have this convergence. Then the sequence converges weakly to the same limit, which is specified by here. So once again, to have this, we need this condition to be satisfied for all L from here. But if we have only dense subset plus norm boundness, then it is enough. And similar statement here. Again, for weak star convergence, we need this condition for all x's in X. But instead, we have only a dense subset in X such that this condition holds, and a norm boundness of the sequence. Then we can conclude the convergence. Then the proof is given as an exercise. It is quite similar. It is quite similar to all things which we have done before. So I skip this proof, but you are welcome to think about it. Okay, and also, of course, you should remember that topological dual is the set of all continuous linear functions. So continuity is important. Okay, so we go further. So it's a kind of criterion for weak or weak star convergence. And we go further. Theorem 10. So let X and Y be two normed spaces, and let A be a linear operator. Then the following statements are equivalent. So first statement is that A is a continuous operator in the sense which we have studied before. So that is as a mapping between two normed spaces. That is, if we have a norm space, we have a topology generated by the norm here and here. So this is a mapping of two topological vector spaces. And then the continuity is defined. For example, that as the mapping is continuous by definition if the pre-image of any open set here is open here. Okay, so continuous in this sense. The second statement, A is continuous in this sense, that is as a mapping of these two topological spaces. That is, here we have strong topology here and here we have weak topology in both spaces. So now they are not norm spaces, but just topological vector spaces. And hence the continuity means that the preimage of open set with respect to this topology, the preimage under this mapping, is open, that is the element of this topology. Okay, so you see these two statements are equivalent. And the third one, which is also equivalent, is as follows. So if we have any sequence in X which converges weakly to X, then it follows that the sequence of images converges weakly to 0 in Y. Yes, so there is a typo, of course, so it converges to 0, and then this converges to 0 as well. So this is a kind of sequential continuity in the point 0 with respect to these weak topologies. Okay, so this is what we are going to discuss. Proof. So let us show that 1 implies 2. So we know that if A, so the assumption is that A is continuous as the mapping of two norm spaces. We know that continuity in this sense is equivalent to boundness. That is, so let norm of A be finite. So any continuous linear mapping is bounded, and any bounded linear mapping of norm spaces is continuous. So consider the following neighborhood of zero in the weak topology. This will be the neighborhood of zero in Y. That is, this is the set of points Y in the space Y, such that absolute value of G1 of Y is smaller than epsilon, etc. Absolute value of Gn of Y is smaller than epsilon. So this is a subset of Y, and we consider epsilon positive and G1, Gn elements of Y star, so topological do. So we have this neighborhood of zero. It's one, so it's a basic neighborhood of zero. Having this, we may consider functionals fi, which are defined as follows. These are gi composed with a. Gi and a, they both are linear mappings, and they both are continuous and hence bounded linear mappings. So a composition of continuous linear mappings is a continuous linear mapping, and it is then an element of X star. So as a picture, probably here. So we have X, we have Y, we have a mapping A. Then GI is a mapping to Y star. And then here we have FI, it's a mapping to X star. And it acts like am I right? Yes, GY is here in Y star. Sorry. I guess. Yes. Sorry. No. Here we have K. Here we have GI, and here we have FI. Okay, so now everything is fine. I mean, either here or here, we obtain the same. Okay, so what we do further, consider another neighborhood of zero, UF1, etc., Fn, epsilon, which is given as follows. So now it is a set in X, such that absolute value of Fi of X is smaller than epsilon for I from 1 till n. So this is a neighborhood of zero here in this topology. So this guy is a neighborhood of zero here in this topology, and this guy is a neighborhood of zero here in this topology. And of course, here you see what does it mean. So what is written here, this is the same as Gi applied to Ax. So having this, we see that A of this set, so the image of this set with respect to A is a subset of this set. So what we have shown? We have shown it only for specific basic neighborhoods, but it is enough. So what we have shown, for arbitrary basic neighborhood of 0 in Y, there is an open set in X, this one. This is an open set in this topology in X, such that the whole image of this open set in X under A lives in this arbitrary given open set in Y. We have shown, hence, that the mapping is continuous. Hence, A is continuous. Okay, in weak topologies. So once again, we have shown not for arbitrary open set from here, but just for a basic open set, so basic neighborhood of 0, but arbitrary basic open neighborhood of 0 in Y. So for any such arbitrary basic open neighborhood of 0 in Y, we have checked this condition, that is, there exists an open neighborhood of 0 in X such that A of this set lives inside of this set. If we have shown for basic neighborhoods, then everything is fine already for all. And hence we have shown the continuity at 0, but due to linearity of A, and due to the fact that these are vector spaces and our topologies are, how to say, shift invariant, if I may say so, then everything is fine everywhere, not only around 0. Okay, so this is just, we have shown that 1 implies 2. That is, if we have continuity in the strong sense, in the sense of norm, then we have continuity in the weak sense, so with respect to weak topology. Let us go further. May I go to the next slide?
Yes, please.
So let us show that 2 implies 3, but it is actually obvious since continuity implies sequential continuity. Oops. We have discussed it somewhere. I have not I don't remember the number of the statement, but we have discussed it definitely in the very beginning of the lecture course. So this is the continuity, and this is the sequential continuity at 0. So this convergence, both convergences, they correspond exactly to these topologies. So if A is continuous with respect to these topologies, then it also sequentially continues. And again, so we have everything happens only in 0, but due to linearity of A, this means that at every point. Okay, and now the most interesting case is that 3 implies 1. Lecture, wait. So in order to prove that 3 implies 1, I need to recall a corollary. I also didn't try to find it, but you may find it yourself. By corollary 4.5, it was lecture number 8. We have the following, this corollary is the following statement. So A is continuous. So as a mapping between topological spaces. If and only if for any sequence xn in X which converges to 0, we have that the sequence AXN, this is a sequence in Y, is a bounded set. So it was a corollary from some statements. So we have A as a mapping between two even norm spaces, and then a mapping A is continuous as a mapping between two norm spaces, if and only if for any convergent sequence. So if A maps any convergent sequence to a bounded sequence. And of course, it is enough to check only sequences which converge to 0 due to linearity of A. So this is what we want to have. Okay, so this is what, so now, so this will be our, how to say, this is the tool which we are going to use, this corollary, that is this statement. And this means that this is our assumption. And we want to show that from this, we obtain this. Okay? This would imply that A is continuous in the sense of as a mapping between norm spaces. So let Xn be a sequence in X which converges to 0 in normal sense, in the norm. This means that the sequence, what's going on? That the sequence of norms converges to 0 as well. Okay? Agree? Triangle inequality. This means that Xn converges, converges to 0, even without triangle because to 0. Okay?
Excuse me.
Yes?
Up to now, I have a question about the item 3. Actually, the notation is weakly convergence.
Yes.
Okay.
Yes. But we okay. So this is our assumption, and this is what we want to show. So let me mark probably. So this is what we have, and this is what we want to show. So what does it mean? We want to show this. So let us consider such a sequence, and let us prove, having this, that we have this statement.
Okay, thank you.
Okay, so this is what we are going to do. So we assume that we have a sequence which converges to 0. So this part is given. And now we want to show this statement, having this. Okay, so we have such a sequence. Hence, the norms converge to 0. Hence, for any L from the topological dual, we have the following. L of Xn, it is smaller or equal than norm of L in the topological dual times norm of Xn in X. Okay, L is a bounded linear functional or continuous linear functional, so this is fixed and bound finite. And xn, norm of xn converges to 0. So all this converges to 0. That is what we have obtained. Xn converges to 0 weakly. So actually, I didn't need to write down this all. I just would say that if we have a sequence which converges to 0 in the stronger topology, yeah, in the topology generated by the norm, then it converges to the same limit in the weaker topology, in this topology, okay? So from this, we have this, actually, because we have already discussed it. But here, so to say, the complete proof of this statement. Okay, but now I use this assumption 3 that this holds. So we have that AXN converges weakly to 0 in Y. And then I use theorem 7-8, which says that if we have a weakly convergent sequence, then it is bounded in the norm. I have no place to write it down, so I need to wait until you are finished, and then I write it down on the next slide. But that's it, actually. So we assume that this holds, hence this holds, hence we apply this number 3, hence this holds. And we have already proved that if we have a weakly convergent sequence, then it is bounded with respect to the norm. And hence we prove what we wanted. May I go to the next slide to finish this?
Okay, please go.
So hence, by theorem 7-8, this sequence is normed bounded. That is, what does it mean? That is supremum over O n in n, axn in y smaller than infinity. And now, okay, so hence by corollary, which we have used for 5, A is continuous. With respect to norms. So in strong topologies. Okay. So you see, so we have norm spaces, and it is somehow natural and useful to work in norm spaces, but sometimes it is easier to deal with convergent sequences in weak topologies. So you see, at least continuity is not violated if we, instead of norm spaces, consider the spaces, the same spaces, but with weaker topologies, with weak topology. Okay, so let us go further. Remark. So let X be a norm space. First statement. So this sigma x star, which is called the weak topology, it is the weakest topology with respect to which all linear functionals from X are continuous. So I recall you that we have this norm space X, and with this topology, then we consider its dual, topological dual, and we have proved that if we weaken the topology here, so if we consider in X not the strong topology, but the weak topology, then its topological dual let me write down like this. Topological dual is the same. So now the question, probably there are some other topologies in between these two, or probably not in between, but probably a topology which is weaker than this one, but still which preserves the same topological dual. Or probably here we may find even a stronger topology instead of this one, such that still the topological dual will be preserved. So the statement is that no. So this is the weakest possible topology, and this is the strongest possible topology, such that the topological dual is exactly this one. Of course, if you weaken the topology, you lose you lose elements from topological duals, because the smaller is the set of open sets here, the more difficult it is for a linear functional to become continuous. Yeah, so the weaker is topology, the smaller is topological dual, and vice versa. The stronger is topology, that is, the more open sets we have in X, the easier it is for linear functionals to be continuous. Yeah, I recall that L maps X into K, and L is continuous if and only if pre-image of any open set. Okay. For any U open in K. Okay, this is a real complex numbers. There is a topology, standard topology. Okay, so the bigger is tau here, the easier it is for a linear functional to be continuous. Yeah, so the strongest topology, the biggest topological dual, the weaker is topology, the smallest topological dual. But nevertheless, there is some amount of topologies such that we play with them, we interchange them, and we still preserve the topological dual. So this is the weakest one, this is the strongest one. The strongest one is sometimes called Marquis topology. Okay, is it clear in general without technical details?
In fact, for me, it's not very clear. I'm struggling with the left graph.
Sorry, I hear you very bad. So I did not understood what you said.
I say that for me, it's not very clear. And I'm struggle with the left graph.
With
Can
this?
you help me? Yes.
Yes. So let me write it down once again. So we have vector space X, and we endow it with some topology. So for example, we take a norm, and then we have a corresponding topology generated by the metric, which is generated by the norm. So this is a topological vector space. And hence, it has its topological dual. So the space of all continuous linear functionals on this space. And this is denoted by X star. Now we consider the space X and take another topology. For example, this one topology. Yeah, and so this is a topological vector space. And we may consider its topological dual, that is the space of all continuous linear functionals on X. Continuous with respect to this topology. Linear functionals, they map X into K. Here we have a fixed topology, standard topology, yeah, on real numbers or on complex numbers. You know what is open ball there, so it's a metric space. There is a topology. But here we play with topology in X. So actually, when we change topology, you just take any topology on X. nobody said that the topological dual will be the same as here. So this is the statement. So when you change topology on X, then this means that you change the space or the set of all continuous linear functionals. So all linear functionals on X which are continuous with respect to this topology. And I said that the stronger is topology, that is, the more open sets there are, the easier it is for a linear functional to be continuous. Because what does mean to be continuous? This means that for any open set in K, so this is how to say, the topology in K is fixed. So we have a fixed amount of open sets in K. But their preimages with respect to this linear functional, they should live in the fixed topology in X. So the bigger is topology tau, the easier is for L to satisfy this condition. That is, the stronger topology tau we have in X, the bigger is the topological dual. Okay?
Yes.
Yes. And now the statement is that for these two topologies, for this one and this one, a miracle occurs in the sense that this topology, in the case of infinite dimensional space, this topology is strictly weaker than this topology. But the topological dual is exactly the same. So this one. Okay? So this is like a good news that we have changed the topology, but we did not disturb the topological dual. And this is a nice property. And there may be some topologies in between these two, which still preserve the topological dual. And now the question, so the statement of this remark is that this topology is the weakest among all possible, is the weakest topology such that the topological dual remains the same. So if we make it weaker, this topology, then the topological dual will be something smaller, not the same. This is this statement. And the second statement is that this topology is the strongest possible, such that this guy is preserved in the sense that, again, if we take a bigger topology, larger topology, stronger topology, then the amount of all continuous linear functionals will increase. So this is the strongest possible, such that we do not perturb the topological dual. So there is no stronger topology which does not generate extra continuous functionals, which are not here. Okay?
This time is for me is okay. It's very clear
Okay.
now. Thanks.
Okay, perfect. So let us go further. Remark 712. So let X be a norm space. So let us summarize good properties of the weak topology in X. Yeah, weak topology in X. So we have just shown in theorem 710 that the continuity of linear operators in the norm, or linear functionals, is the same as continuity in the weak topology. So continuity in the norm is equivalent to continuity in the weak sense, in the topologies, in the weak topologies. Second good property, quotient. So we have this statement. It works for this topology and this topology, but this statement does not necessarily hold for topologies between. So nobody said that there is nothing in between. Probably there is. It depends on particular spaces. Okay. So it's really a very nice result. So we have two different topologies. One is, so in the infinite dimensional situation, one is strictly weaker than the other, but the continuity in both senses are equivalent. Okay. Next good property. So boundness in the norm is equivalent to the boundness in this topology. That is our transition from the strong topology to the weak topology preserves continuity and preserves the set or amount of bounded sets. Before discuss it, we need to clarify what does this mean. What does mean boundness in this topology? So for this definition, so let X be a norm space, M a subset of X. So the set M is called weakly bounded, that is bounded in this weak topology, if the following holds. That is supremum over all points in M of coordinates given by the topological dual. So supremum of absolute values of all coordinates, supremum over all points of M is finite. Yeah, so instead of having norm of X, yeah, this would be bounded in the norm. Now we have this. Okay?
Okay.
So theorem M is weakly bounded if and only if M is norm bounded. And the proof is again exercise, but everything is very similar to what we have already done today. So we use the uniform boundness principle, and we from points of M we go to these point evaluations, which are elements of X2 stars. Okay. To exercise, just using all arguments which we have presented today, prove this statement. Good. So once again, we have normed space. We have made a transition from strong topology to weak topology, and nice properties, continuity is preserved, boundness is preserved, and moreover, what is also very important, if we have sets which are both convex and closed, then this convex plus closed in the sense of the norm is equivalent to the convexity and closeness in the weak topology. And this is what we are going to show right now. For this, we need this theorem, which we are going to present right now. So, but nevertheless, please remember, so this is like a summary, what we can preserve in spite of changing the topology in a proper way. Of course, this everything works in these particular cases of this topology and this topology. That's why it's a very nice topology. Okay, so theorem 713. So let X be a norm space over R. V be a convex set in X. Then the statement is that this set is closed in the weak topology if and only if it is closed in the norm. Of course, convexity, I hope you remember what does mean that the set is convex?
Yes. For
Yes.
each 2 points in V, the linear combination, maybe the special linear combination is
Convex.
there in it.
Yeah, so the whole interval between them is in V, yes. So for convexity, we need only linear structure of X. Yeah, convexity is defined only in terms of linear structure. We don't need any topology. So the set is convex, it is convex in X in spite of any topology. And now the closeness. So we cannot, so remember, so once again, let us remember that in infinite dimensional situation, so this topology is strictly stronger than this topology. What does it mean? That we have more open sets here than here. But this means that we have more closed sets here than here. You see? So without convexity, we cannot prove anything like this, because in infinite dimensional situation, weak topology is strictly weaker than this one. But then the miracle occurs, and if V is not just a set, but a convex set, then closeness in weak topology for a convex set is the same as closeness in the norm. And this is somehow in the direction of convex optimization, which like a hint, which this statement is a kind of hint that in the case of convex optimization, everything should work nicer. Okay. So this is the theorem. This is the statement. Moreover, V coincides with the so if V is convex and closed in any of these senses, this means that V coincides with the intersection of all closed subspaces of the form. So it's like a half spaces. Half spaces given by continuous linear functionals and real constants. So V is an intersection of all closed subspaces of this form, which contain V, of course. So not for all L and all C, but for such L and C that each such subspace contains V. Okay, so this is the statement. Let us try to prove it. It is not a very long proof, so let us proceed with the proof, and then this would be somehow the last thing for today. Okay, so proof. Let us show this direction. That is, we have this statement, let us show that this holds. So let V be, so to say, norm closed. So let U be a point which does not belong to V. Now we use the theorem of Hahn-Banach, of course. By corollary, it was corollary 5.27, lecture 12. And I guess I even have it here. Let me check. Lecture 12. So corollary 5.27. Here it is. We have a norm space over R, V a convex and closed, and a point which is not in V. Then there exists a non-trivial linear functional, continuous linear functional, which separates this set and this point. Separates in this sense. And we have strict inequality. Okay, so this is what we are going to use in our proof. So by this corollary, there exists a linear, non-trivial linear functional x L from x star, which satisfies the following condition. L of U is bigger than the constant C, which is exactly the supremum of L of V over all V from this set V. So V is norm closed. U is a point which does not belong to V. So by Hahn-Banach, we may separate them by a suitable linear function. And so now let us interpret this separation. That is what we have shown. We have shown that V belongs to the set, let me call this set PU, which is the set of all x's in X, such that L of X, so this L, exactly this L, such that this L of X is smaller or equal to C, with exactly this C. And we also know that U, the point U, does not belong to this PU. Yes, because L of U is strictly bigger than C, and PU is the set of all points where L of X is smaller or equal to C. And U does not belong to PU. Okay, agree?
Yes.
Yes. Okay, moreover, I can rewrite this set as follows. This is the set is the pre-image of this interval. Okay.
Yeah, by definition.
Yes. Hence, this set is closed with respect to this weak topology. Yeah, so L belongs to this topological dual. This guy is topological dual both for this space and for space X with this topology. Yes, so any element from this set, so any L from here, is a continuous linear functional also in this sense with respect to this topology. And hence the pre-image of a closed set should be closed with respect to this topology. And this set is closed because its complement looks as follows, and this is an open set. So
Yes, it's clear.
yes, clear. Okay, perfect. Okay, so what do we have then? Hence, I can represent V as a, so V belongs to an intersection of all PU over all U not in V. So how I have constructed this PU? I have taken any arbitrary point U which is not from V. Starting from this point, I have constructed a corresponding linear functional. Yeah, of course I'm not sure that it's a good idea, but of course I may like add this U everywhere. Yeah, just to specify that all this L and C, they depend on U. And so for arbitrary fixed point U, which is not from V, we have obtained this statement. So I can repeat this construction for any other point, and hence, and obtain the same statement. And hence, V belongs to the intersection of such guys over all points which not belong to V. Agree?
Yes.
Yes. Moreover, we see that this set PU is closed in this sense. Hence, intersection of closed space sets, intersection of closed sets is again closed. Yeah, by properties of closed sets is sigma x star closed. Yeah. Oops. As intersection of sigma x star closed sets PU. Okay, so V lives in this set, and this set is at least closed. Moreover, we see that V complement intersect with this nice set PU is an empty set. Yes, because so you see, we take any U which does not belong to V and we construct PU such that V belongs to PU and U does not belong to PU. This means that when we consider such intersection, for any element from here, for any U from here, that is a U which does not belong to V, there exists the corresponding PU which does not contain this U. And hence intersection again does not contain this U. Okay, so is it clear?
Yes.
Okay, but this means that my V is exactly this intersection, not only a subset, but exactly that. And hence V is sigma x star closed. Okay, so we have shown this implication. So if V is closed in the sense of the norm, then it is closed in this topology.
Mhm.
Okay. So once again, we have used here implicitly that in both topologies we have the same topological dual space. Okay, let us go further. Let us prove the opposite direction. So let V be closed in this topology, weak topology. But we know that this topology is not stronger than the topology generated by the norm, since this topology x star is weaker than the topology generated by the norm. That is, in the case x is finite dimensional, these two topologies coincide. If x is infinite dimensional, then this topology is strictly weaker than this topology. But what this means? This means that all open sets from here are also open sets from here. And all closed sets from here are also closed sets from... Okay, closed sets in this topology means that the sets whose complements live in this topology, are open, live here. Yeah, so since we have this inclusion, then V is also closed in this topology. So these two topologies are comparable. This is a stronger one. That is, it contains more open sets, but nevertheless, all open sets from here, they also belong to this system of sets. And hence all closed sets, that is, sets whose complements live here, yeah, this means that these complements live also here, that is, they are closed also in this topology. Okay?
Okay. This direction is trivial.
Yes. Okay, just the last remark for today. So if X is not reflexive, the statement of theorem 713 is not true for the weak star topology on X star. So I mean, yes, here we deal with weak topology. Of course, one could think about working with X star and weak star topology on this set. Because before we had some statements where we had item I for X and item 2, something similar for X star. Here weak topology, here weak star topology. We had something like this. But this statement is as it is, only for weak topology in X. And if X is not reflexive, this statement does not work for weak star topology on X star. Why? Because here we used this corollary. This corollary means that we work in X and we consider its topological dual. That is, if we would work here, we use corollary, we need to work with its topological dual. This is X2 stars. And this does not correspond to the weak star topology, because for the weak star topology on X star, we deal with only linear functionals from here, not from here. So if X is not reflexive, this space is bigger than this space, and hence this corollary would not work. So once again, with other words, if X is not reflexive, weak star topology on X star is strictly weaker than the weak topology on X star. And hence, what is true for weak topologies does not need to be true for weak star topology. Okay, so I guess that's it for today. You have a lot of things to think about or try to prove the exercises. And we finalize this topic next time. So do you have any questions or comments?
No questions. Today, I think it's very clear and
Perfect.
fruitful.